0.01 Celsius, which is chilly, but I mean, it's been chillier this winter at times, so that's no big deal. But check out what this means. This means that all three phases coexist at this point. You're at this pressure and at this temperature, all three phases are what we call in equilibrium. So here, solid and liquid are in equilibrium, anywhere along this line. Liquid and gas are in equilibrium along this line. Solid and gas are in equilibrium. But here, all three can coexist. So yes, you could have, in a tube that has been with the right pressure and the right temperature, you could have some ice, water, and steam at the same time. It's really cool. So the triple point is, technically speaking, the pressure and temperature at which all phases of matter coexist specifically in equilibrium. Now I know the term equilibrium, aside from the bio stuff, doesn't mean a ton to you at this point. I get it. But at the same time, I want you to write it down because it will mean something to you in the next couple of chapters when we talk about equilibrium a little bit more formally. Now, a couple more things to talk about, and that's critical temperature and critical pressure, and then the critical point is just a combination of those two, so that's pretty simple. Let's take a look. See this critical point right here. There's a pressure and a temperature associated with it. Well, what this actually means, this phase diagram actually continues beyond 225 atmospheres and beyond 374 degrees Celsius. But here's the deal. At 374 degrees Celsius and higher, you can only have a gas. So this graph would actually go vertically right here, straight up to infinity. Because above 374 degrees Celsius, the molecules, I should say, of water are moving so fast that there is no way for them to get close enough to be a liquid or a solid. And so above 374 degrees, that's it. It's all gas out here, beyond the critical point. So you can actually think about it being a vertical line, as vertical as I can do one right here, right there, straight up, off the page and forever, okay? So let's write some of this, let's write some of this down. The critical temperature is the temp above which only gas can exist. Now, even at that temperature, if you're at 374 degrees Celsius, most of the time it's going to be gas. You need to put an awful lot of pressure on this gas in order to get those molecules close enough to each other so that they act like a liquid. So at 374 degrees Celsius, it takes this much, 225 atmospheres for water. And again, every substance is different. You don't have to memorize any of that. Just have to understand the shape of the diagram and where the lines are and what all the points are. But at 225 atmospheres, that would be considered the critical pressure. And that would be the pressure that you need to make a liquid when you're at the critical temperature. So let's write that down. Critical pressure. The pressure required to make a liquid at the critical temperature. Really the critical temperature that's running the show here. Critical pressure is just the added piece of information you need. The critical point is just the pressure and temperature combination. Above which, I should say. How do you say that? It's really, I know you don't want me to erase it. The pressure and temperature. Sorry, got to erase it. The point on the graph at which the critical temperature and critical pressure meet. It's really just a point on a graph right here. That's all it is. Quite straightforward. But that critical point, it's like a coordinate on the graph, describes the whole thing. So there you go. There are the definitions. You have the phase changes that we had on page 2, phase diagrams on page 3. You'll have a chance to do a couple of problems in class, dealing with those from your problem set, from your homework sheet, and we'll go from there. Have a great night.